Right now, your phone is receiving signals from at least 7 satellites. It needs to determine 3 numbers: latitude, longitude, and altitude. That's 7 equations, but only 3 unknowns, and every measurement has noise. No exact solution exists. Your phone doesn't throw away equations. It uses all of them by solving a system that technically has no solution. Today, we'll see how multiplying by a single matrix transforms an impossible system into one with a unique best answer. To understand how, let's start with what no solution looks like. Consider a system AX equals B, where A is a 3x2 matrix and B is a vector in R3. A has 2 columns, so AX produces linear combinations of those 2 columns. The set of all such linear combinations is called the column space of A. Geometrically, this is a 2-dimensional plane passing through the origin in 3-dimensional space. Now, if B lies on that plane, the system has a solution. We can find some x that produces B, but if B sits off the plane, no choice of x can produce B. Ax equals B has no solution. This is what overdetermined means. More equations than unknowns, and generically no exact answer exists. So what do we do instead? We look for the closest point on the plane to B. That closest point is called P, which equals A times x hat, where x hat is our best approximate solution. The error vector E equals B minus P, and it drops perpendicularly from B down to the plane. Finding its closest point requires setting up a different system of equations. Here's the key move. We start with AX equals B, which has no solution. Now, multiply both sides on the left by A transpose. We get A transpose A times x hat equals A transpose B. This is a very important equation, so let's box it up. It's called the normal equations. Now, let's watch the dimensions carefully. A is m by n, so A transpose is m by m. The product A transpose A is m by m times m by n, which gives us m by n, a square matrix. On the right side, A transpose times B is m by m times m by 1, which gives us m by 1, a column vector. So look at what we've done. Right? We transformed a rectangular overdetermined system into a square one. The normal equations always have at least one solution, even when the original system had none. Multiplying by A transpose projects B onto the column space of A, creating a system we can actually solve. Let's compute with a concrete example. Take A as the 3x2 matrix with rows 1, 1, then 1, 2, then 1, 5. The first column is 1, 1, 1, and the second column is 1, 2, 5. These columns are linearly independent because neither is a scalar multiple of the other. A transpose is the 2x3 matrix with rows 1, 1, 1, and 1, 2, 5. Now let's multiply A transpose times A. For entry 1, 1, we compute 1 times 1 plus 1 times 1 plus 1 times 1, which equals 3. For entry 1, 2, we compute 1 times 1 plus 1 times 2 plus 1 times 5, which equals 8. For entry 2, 1, we compute 1 times 1 plus 2 times 1 plus 5 times 1, which also equals 8. And for entry 2, 2, we compute 1 times 1 plus 2 times 2 plus 5 times 5, which is 1 plus 4 plus 25, equaling 30. So A transpose A equals the 2x2 matrix 3A, A30. Notice it's symmetric. Both off-diagonal entries are 8. Now let's find the determinant. 3 times 30 minus 8 times 8 equals 90 minus 64, which equals 26. That's non-zero. So A transpose A is invertible. This is no coincidence. The independent columns in A produced an invertible A transpose A, which guarantees a unique least square solution, x hat. A transpose A gave us a square system, but it's not always invertible. 3 important properties hold in general. First, a transpose A is always square. If A is m by n, then A transpose is m by m, so A transpose A is m by n, always a square matrix. Second, a transpose A is always symmetric. To see why, take its transpose. the transpose of A transpose A equals A transpose times A transpose transpose, but A transpose transpose is just A again, so we get A transpose A, the same matrix we started with. That confirms symmetry. Third, and most important, a transpose A is invertible if and only if A has linearly independent columns. This means the null space of A contains only the zero vector. Equivalently, the null space of A transpose A equals the null space of A. This third property needs proof, and the argument reveals something deep. We'll explore that next. The proof rests on one key fact. The null space of A transpose A equals the null space of A. We prove this in two directions. Forward direction, suppose AX equals 0, meaning X is in the null space of A. Then A transpose AX equals A transpose times AX, which is A transpose times 0, which is 0. So X is also in the null space of A transpose A. This shows that the null space of A sits inside the null space of A transpose A. The reverse direction is subtler. Suppose A transpose AX equals 0. We cannot simply cancel A transpose because A transpose is rectangular and not invertible. Instead, we use a clever trick. Multiply both sides on the left by X transpose. The left side becomes X transpose A transpose AX. Now here is the key insight. We can rewrite X transpose A transpose as the quantity AX transpose. So the left side becomes AX transpose times AX. This is the dot product of the vector AX with itself, which equals the squared length of AX. The right side is X transpose times 0, which is just 0. So the squared length of AX equals 0. But a squared length of 0 forces the vector AX itself to equal 0. Since the only vector with 0 length is the 0 vector, therefore X is in the null space of A. This shows the null space of A transpose A sits inside the null space of A. Combined with the forward direction, both null spaces are identical. Same null space means same rank by the rank nullity theorem. So A transpose A is invertible exactly when A has linearly independent columns. Now let's see what happens when this condition fails. We'll compare our earlier independent column example on the left with a dependent column example on the right. On the left, we have the independent columns case with rank 2. Our matrix A is the 3 by 2 matrix with rows 1, 1, 1, 2, and 1, 5. A transpose A came out to the matrix 3, 8, 8, 30 with determinant 90 minus 64, which equals 26, not 0. So A transpose A is invertible and a unique X hat exists. Now on the right, consider the dependent columns case with rank 1. Take A to be the matrix where every row equals 1, 3. That means column 2 is 3 times column 1. The columns are dependent. Now compute A transpose A. We get the matrix 3, 9, 9, 27. Notice that row 2 is 3 times row 1. The dependency carries over. The determinant is 3 times 27 minus 9 times 9, which equals 81 minus 81, which is 0. So A transpose A is singular. The normal equations have no unique solution. This comparison makes the theorem concrete. Independent columns gave a determinant of 26 and a unique X hat, while dependent columns give a determinant of 0 and no unique X hat. Now let's come back to your phone and see the full picture. Your phone receives noisy distance measurements from multiple satellites. It sets up the system AX equals B, but there are far more equations than unknowns. This means the system is overdetermined and no exact solution exists. So what does it do? It forms the normal equations. A transpose A times X hat equals A transpose B. The satellite geometry gives independent columns as long as the satellites aren't all clustered in a line. So A transpose A is invertible. The solution is X hat equals the inverse of A transpose A times A transpose B. The X hat is your position on the map, a pin drop on the globe. Now here's the bigger picture. These normal equations are the algebraic backbone of least squares regression the most widely used method in statistics, machine learning, and engineering. Every time you fit a line to data, estimate model parameters, or run a linear regression, this is the underlying machinery. And the key question, when does A transpose A have an inverse, is really the question. When is our best approximation unique? The answer, when the columns of A are independent. Good satellite geometry means independent columns, which means A transpose A is invertible, which means a unique best position estimate.